Today's video is going to be on data representation, namely tables, graphs, and the regressions you get from the graphs. And those are three different ways that we can represent the data sets that we collect from our experiments. In addition to that, we're going to be focusing on the graphical mathematical models and looking at what success criteria we have for making those, meaning like what are the characteristics that we find valuable when we are sketching out those graphs or writing those models so that we can include those on our whiteboards or in our findings. So to start right off, a lot of times when you guys are collecting data, the natural tendency is to go right to tables. And that makes sense because we're just recording our data. It's kind of like a T-chart here, you know, where you have like your X and your Y axis, right, or your values, your independent, dependent variables. So say, you know, for example, you may have like, you're writing down, you're like, okay, I'm going to pick a value for 2, and maybe that's like 6, or then you go to 4, and that ends up being 9, and then 6, and that being 12, and so on, and you just collect a lot of data. I'm not saying what's good about data, I'm just showing you what this might look like on a whiteboard. Okay? Now, tables for us are not going to be really that valuable. To just put it briefly, when we are collecting data, I don't really care about all these individual numbers when I'm trying to see a relationship. In fact, seeing the data like this prohibits me from seeing the relationship. I'm looking more at like points, which is natural human tendency. I see numbers, I'm trying to see if this number fits my expectation, right? Like if I were to all of a sudden get like 11 here, that may throw me off, and I may want to repeat that because I don't expect that value, and that's bias. We don't want to do that. So we don't want to look at necessarily the point-to-point reasoning when we're trying to figure a relationship. We do want to look at the point-to-point, like each point individually, when we're looking at error. So what we're going to say here is that, smiley face, tables can be good for repeated trials. Because in repeated trials, I'm looking at the individual points that should be identical and trying to see if they're not. So this allows me to then, I can get an average. And what's more important about this is I can get a range of error, or what I tend to call this is uncertainty, but there are a lot of measures for error when you take a statistics class, but we're just going to keep it really simple and just do this equals the highest value of our repeated trials minus the lowest. Okay, so for example here, what I would want to do is say, okay, well, let's say for this one I did 6.0, 6.2, 6.4, 5.8, right, and 5.6. Now this would be the repeated trials, right? And so for example then, what I would want to show is that the average value was 6, and the range of error, which I take the highest minus the lowest, so 5.8 was the lowest, or sorry, 5.6 was the lowest, 6.4 was the highest, as a difference of 0.08. Or sorry, 0.8. So that like is what we want to find important. And if you're including stuff on the whiteboard, I would just use 6 on my chart, right? Because I would use the average as that single value. When x equals 2, y equals 6. That's what we found on average. But I want to report this error because that shows how much fluctuation we had in the values that we tested at 6. Okay, the rest of this blue I don't really care about. So you really could just put 6 into a graph, right? And then just on your whiteboard say that, hey, due to repeated trials, I found an error that's approximately 0.8. So why do tables? You actually don't, because we have software now like graphical analysis or Excel sheets, your TIs, calculators, that you can just type these numbers directly into it while you collect data instead of writing them down and then typing them in later. So it actually makes more sense to go right to a graph. Graphs are going to allow us to see the relationship, as I'll mention here in a moment. Okay, so on a whiteboard we can't include a scale graph because scale graphs are coming from our computers. So how do we record them onto like a piece of paper, onto our little whiteboards? I have this example here, which is I just did like the volume of gas, so I used 1 gallon of gas, and then I just looked at how many miles I was able to travel. Then I would use 2 gallons of gas, we'll look at how many miles, and so on. And I just plotted these. So instead of writing down a table, I just recorded that table, right? And if you did repeated trials, you could put this off the side. Like I did 1 gallon of gas, 6 times, and the average was 20, but I added a give or take 3 miles, let's say. So I could record outside, and I can show the repeated trials for that 1 gallon of gas value. But you don't have to necessarily show the chart here. Okay, so what I really want to see is this. Now this looks like a straight line to me. So as the experimenter, I'm going to do a curve fit and choose this to be linear. Now we can choose a lot of different things here. In our class, we're pretty much going to focus on linear and quadratic. This being that a linear one. When I hit apply, it does a regression for me. So what do I then show if I want to say, here's the graph I got, and I can't show my computer screen necessarily, then how do I abbreviate this and kind of sketch it onto a blank whiteboard or paper? Okay, so this is going to be graphical models. Okay, so graphical models right out of the gate, why they're good is this allows us to see the relationship by the shape of the curve. So let's say we never even saw the table yet. And what you're seeing for the first time is the graph. So we're going to have distance traveled, that was in miles. And we had the volume of gas, and that was in gallons. So that's important to put on there because we want to make sure we label the y-axis, right? So that's an important criteria right there, is to label the x and y-axis with what you're measuring. That shows the independent, dependent variable. It shows the unit you're using. So that's an important feature. And obviously the most important thing here is going to be, what is that relationship? And I found it to be direct. I found it to be a linear regression model that would fit this data. So this would basically be done, except that I want to provide some kind of scale. So if this is 0, then what was this? And we ended up using, if we look back, about 10 gallons of gas, and I went to about 225 miles. So I'm just going to put down 10 here and 225. What I want to make sure that you don't do is do not do this. Okay, that's pointless because this graph isn't to scale. If the graph is not to scale, then it doesn't matter. So I'm going to say again because it's wrong. This is not on graph paper, so it doesn't matter where the points are. Okay, all I want to know is what trend did it follow. Okay, and with that, then we can get an idea of the relationship, right? It's a direct relationship, a linear relationship, and I get that a feel for scale then by putting the max value. So I can be like, oh, this group went to 10 miles. Maybe some other group went to 100 gallons. I don't know how you get that gas tank, but it doesn't matter. So like what kind of range of volume did you use for your independent variable? So this would be an example of from that one. So in more general terms, like what are the success criteria, right? So it's success criteria. These are like what are the things I would grade, okay? So for a graph, what I would be looking for if I were grading this would be label, units, label units, max value, and the trend line or curve. And I do not want points. I'm not going to mark off, very likely. if you put points on there, but I don't want points since this is not a scale. Okay, so this would be our success criteria. So the other thing I want to put on the whiteboard, in addition to this kind of graph, so you can see here as an example what it should look like for our data that we just collected, I also want to put a mathematical model. Jump down to this other page here. This would be the regression model in algebra. You guys have studied it. So now what these are going to be good for is, unlike the graphs that allow us to see the relationship really well by the shape of the curve, these are going to be much better at allowing us to make predictions. So I'm going to say it's good for making predictions algebraically. So it's really good for making predictions algebraically. You can make predictions by interpolating and extrapolating your data on the graph. For example, if I want to look here and say, well, okay, how many gallons of gas do I need to go 100 miles? So then I'd look at 100 miles, go over to here, my best fit line, and I'd say, oh, I need about 4.5 gallons, right? Or if I want to say how many gallons of gas do I need to go 300 miles, I'd have to like extend this graph and extrapolate out, right? So you can do it, but a lot of it's going to be eyeballing off the graph. Whereas if I use the regression model, I can make a prediction with this y equal to mx plus b. So in math class, for example, we're going to write it like this, right? We would write, given our data, which had a slope of 22.7 and a y-intercept of negative 2.7, we would write it like this. Y equals 22.7 times x minus 2.7. This is math class. Nothing wrong with it, okay? But in physics class, for us, because it's an experiment, what I want to make sure that we write this is in the following format. This is going to help us during our discussion of our results. We're going to be writing then, instead of y, we're going to be writing d. Okay, this is an example. Why d? Because we get distance on there. We're going to replace what's on, we're going to replace y with what's on the y-axis. Okay, slope stays the same. And x, we're going to replace x with what's on the x-axis. That was volume, so we're going to use v. And then minus 2.7. We'll leave the numbers as is for now. But that would be our mathematical model. Okay, so this would be, for example, what we'd write. So we want this. Okay, the success criteria we are going to replace y and x with the variable for what is on each axis. That's kind of hard to explain, but that would be like right here and right here. Okay? The other thing that I'm going to want you to do is to focus in on these numbers a little bit. In particular, what I want you to do is to write this slope out as a rate, meaning as a fraction. I'm going to come back to that a lot more in the next class, but we want to, if linear, write out slope as a rate with units. So for example, this would be 22.7 over 1, and I would put units on that, which is going to be how many miles you have per gallon. Now we can figure out what that exactly means. Okay. Thanks, everybody. See you in class.